Hey there guys, welcome to my walkthrough of the 2018 Edexcel new A-Level Maths Paper 3, which is Statistics and Mechanics. So, slight change of format here. I'm going to do Section A in this video, which is the Stats, Section B in the next, which you can find linked below, as well as the paper, mark scheme, large data set, and all of my other A-level content, including all past papers from all exam boards. So, let's go. Okay, question 1. Helen believes that the random variable C, representing cloud cover from the large data set, can be modelled by a discrete, uniform distribution. So discrete means countable, uniform means all outcomes have the same probability. Part A wants us to write down the distribution of C. So, in the large data set, cloud cover is measured by octas. Now an octa is 1/8 of the sky. So all the possible outcomes are 0 octa up to 8 octa. So altogether, C can take 9 values. So 0, 1, 2, 3, 4, 5, 6, 7 and 8. Now it's uniform, all the probabilities are equal, so they're all going to have to be 1/9. Cool. Part B says, using this model, find the probability that cloud cover is less than 50%. So, for that then, 50% would be 4 octa, so we want the probability C is less than 4, which we can see C could be 0, 1, 2 and 3, so that's 4 lots of 1/9. So it's 4/9, which is approximately 0.444. Cool. Okay, then Helen used all of the data from the large data set for Han in 2015 and found that the proportion of days with cloud cover of less than 50% was 0.315. Part C wants us to comment on the suitability of Helen's model in light of this info. So, 0.315 is quite far below 0.444. So, far lower than expected. Now, because of this, the model is bad. We wouldn't necessarily expect it to be exactly 4 nights, but it should have been a lot closer than 0.315 if the model was reliable. Okay, then part D wants us to suggest an appropriate refinement to Ellen's model. So I would say the biggest problem is that she had a uniform distribution. We know from life that cloud cover is going to depend on where you are and also what time it is. So the refinement would be to use a non-uniform distribution. Cool. Okay, question 2. Tessa owns a small clothes shop in a seaside town. She records the weekly sales figures, £, and the average temperature 2 degrees C for 8 weeks during the summer. The product moment correlation coefficient for these data is minus 0.915. Okay then, for part A, stating your hypotheses clearly and using a 5% level of significance, test whether or not the correlation between sales and average weekly temperature is negative. Okay, so first up then, for our hypotheses, H0 is going to be that there is no correlation. So for H0, P is equal to 0. Now, what we are testing is whether or not the correlation is negative. So H1 is that P is less than 0, so negative. Now, we are using a 5% level of significance. So if we draw a diagram, then we're going to have a critical value here such that the area here is 0.05. Now, in this region, we accept H1 if our critical value is in here. We accept H0. So remember that she took data for 8 weeks. So our sample size is 8. Now, in the formula booklet and the stat tables, we have one for finding critical values for correlation coefficients. It's on page 37. So, along the top, we have the level. So we have 5%, so we want 0.05. And over here, we have the sample size n, so we want 8. So we're on this row here, and then we want significance of 0.05, so that gives us 0.6215. Now, we then or on the left hand side, so this value is minus 0.6215. Now, our coefficient is minus 0.915, so minus 0.915 is less than minus 0.6215. So, that means then we accept H1, there is evidence to suggest at the 5% level that there is negative correlation. Go. Okay then, part B wants us to suggest a reason for this correlation. So, think about it logically. This is saying as temperatures increase, sales decrease. She lives in a seaside town, so do I, and I can confirm when the temperature is hotter, we spend less time in the shops, more time at the beach. So that would do it. So Tessa suggests that a linear regression model could be used to model these data. Part C, state giving a reason whether or not the correlation coefficient is consistent with Tessa's suggestion. Okay, so with the correlation coefficients, remember that if R is equal to 1, then we do have positive correlation. It would be a straight line. As R gets closer to 0, the data get further and further away from a line of best fit. And if we equal 0, there is no correlation at all. On the flip side, if R is equal to minus 1, then the points lie on a straight line with negative gradient, and as we get close to 0 again, the points get further from the line of best fit. Now, R is, for us, R is minus 0.915, so minus 0.915 is very close to minus 1. So, linear regression is appropriate. If we had a value that was far above minus 1, not so much, but our value is quite close. Part D wants us to state giving a reason which is likely to be the explanatory variable. So, the explanatory variable is the one on which the other variable depends. So, does the temperature care about sales of clothes? No. Does the sale of clothes depend on the temperature? Well, our correlation coefficient suggests yes. So, T is the explanatory variable because sales of clothes likely depend on temperature. Cool. Okay, then Tessa calculated the linear regression equation as W is 10,755 minus 171 T. Part E, give an interpretation of the gradient of the linear regression equation. Okay, so the gradient is minus 171. So if T is 1, we would get 10,755 minus 171. If T was 2, we get 10,755 minus 171 times 2. So what this means is for every degree increase in temperature, we lose 171 pounds of sales. So for every degree increase, Tessa loses 171 pounds of sales. Cool. Okay, question 3. In an experiment, a group of children each repeatedly throw a dart at a target. Sounds dangerous. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. Peter models h as being binomially distributed where n is 10 and p is 0.1. Part A answers to state two assumptions Peter needs to make to use her model. Okay, so with the binomial distribution, events must be independent. So she must assume that each dart thrown is independent of the others. Now for the second one, for binomial distribution, you need a constant probability. So your probability is not allowed to change. So she also needs to assume a constant probability of hitting the target. Now think about what we're doing. We have got different children throwing darts at a target. So not only is it from dart to dart, but also child to child. So this must be true from dot to dot and child to child. Cool. Okay, part B. Using Peter's model, find the probability h is greater than or equal to 4. So, using our calculators, this is nice. So if we want the probability x is greater than or equal to 4, h is greater than or equal to 4, we don't want 3, 2 and 1. So, on our calculator, using binomial CD, that always works out the probability up to and including the value that we put in. So, the probability h is greater than or equal to 4 is 1 minus the probability h is less than or equal to 3. Now, go into your menu, press 7 for distribution, down 1, binomial CD, 2 for variable, put in x is 3, n is 10, and p is 0.1, and you will get 0.2 seconds and 9872. And that gives us 0.0128. Cool. Okay, next up, the random variable f represents the number of the throw on which the dart first hits the target. Using Peter's assumption about this experiment, find the probability that f is equal to 5. So, that means we want the child to miss 4 times and then hit on the 5th time. So, the probability that f is equal to 5. Now when you're doing successive events, you multiply the probabilities together. So 4 misses in a row is 0.9 to the power 4. So there are our first 4 misses. Then we want to hit. The probability of hitting is 0.1. And that will give us 0.06561. Cool. Okay, next up, Thomas assumes that in this experiment, no child will need more than 10 throws for the dart to hit the target for the first time. He models the probability f is equal to n as the probability f is equal to n is equal to 0.01 add n minus 1 times alpha, where alpha is a constant. Part D wants us to find the value of alpha for 4 max. Okay, so we know in a probability distribution, all the outcomes, or the probabilities of all the outcomes, must add together to 1. So we can say the sum for n equals 1 to 10 of the probability f is equal to n is equal to 1. So that means then we've got a big distribution to draw, sadly. So I'm going to do it vertically, so we'll have n and the probability f is equal to n there. So when n is 1, the probability f is equal to n is 0.01 and 0 alpha. So that's 0.01. When n is 2, we get 0.01 and 1 alpha. 3, we get 0.01 and 2 alpha. And then we get 0.01 and 3 alpha. Halfway there, 6, so we get 0.01 and 5 alpha. Almost there, and then for 10 we get 0.01 and 9 alpha. Now we know then that all of these probabilities on the right added together add up to 1. So we've got 10 lots of 0.01, which is 0.1. Now then, how many alphas? So we got 1, 3, 6, 10, 15, 21, 28, 36, 45. So 0.1 add 45 alpha is equal to 1. 45 alpha is equal to 0.9. Alpha then is equal to 0.9 over 45, which is 0.1 over 5, which is 0.02. Boom. Okay, then for part E, using Thomas's model, find the probability that f is equal to 5. So now that we know alpha, probability f is equal to 5 is 0.01 add 4 times 0.02, which is 0.09. Cool. Okay, then part F wants us to explain how their models differ in describing the probability that a dart hits the target in this experiment. So, think about Peter's model. We said for her to use binomial distribution, the probabilities had to be independent and constant. Now, in Thomas's model, the probability is 0.01 and n minus 1 lots of 0.2. So, as n increases, then by Thomas's model, so too does the probability of hitting the target. So that is how they are different. Peter's model has constant probability, Thomas's has increasing probability. Okay, question 4 is a whole page. How exciting. So, Charlie is studying the time it takes members of his company to travel to the office. He stands by the door to the office from 8:40 to 8:50 one morning and asks workers as they arrive how long their journey was. Part A, state the sampling method Charlie used. So, he's just asking whoever is around to ask. So, we call this either opportunity sampling or convenience sampling. Same thing. Okay, then part B wants us to state and briefly describe an alternative method of non-random sampling that Charlie could have used to obtain a sample of 40 workers. Okay, so this one would be quota sampling. So, for example, Charlie could have taken a sample of a certain number of people at time intervals. So he could have sampled 2 people every 5 minutes, maybe, or done 8 people each morning for the week. Something like that. Cool. Okay, next up, Teruni, awesome name, decided to ask every member of the company the time X minutes it takes them to travel to the office. Part C wants us to state the data selection process Teruni used. So, when you ask everyone, that is census sampling. So you're asking every single person, it's census. Okay, next up, Teruni's results are summarized by the box plot and summary statistics below. So, on the box plot, the 2 stars on the right, remember that they represent outliers. We're told that N is 95, so there's 95 people working in the office. The sum of X is 4,133, and the sum of X squared is 202,294. Part D wants us to write down the interquartile range. So, the interquartile range is the difference between the upper quartile, which is there at 58, and the lower quartile, which is here at 26. So, 58 take 26 on a good day is 32. Cool. And part E for 3 marks wants us to calculate the mean and standard deviation. So, because we're dealing with a population, really we should use mu. So, mu is sigma x over n, which is 4133 over 95. Now that gives us 43.51. So I would always at least go to 2 decimal places. And now the standard deviation sigma, you're given the formula for it. So it's the square root of sum of x squared over n minus the mean squared. So we're going to get the square root of 202,294 over 95 minus 43.51 squared. And that, to 2 decimal places, gets us 15.37. You may get slightly different answers depending on your level of rounding. Cool. Okay, then part F, state giving a reason whether you would use the mean and standard deviation or the median and interquartile range to describe this data. So again, as mentioned earlier, these 2 stars are outliers. We can see that they're really far away from most of the data. So what they are going to do to the mean and standard deviation is make them bigger than really we would expect. So they're going to skew the data. So in light of that, we would be better off using the median and interquartile range. Okay, then for the final part, Rana and David both work for the company and have both moved house since Taruni collected her data. Rana's journey to work has changed from 75 minutes to 35 minutes, and David's journey to work has changed from 60 minutes to 33 minutes. Taruni drew her box plot again and only had to change 2 values. Part G. Explain which 2 values Taruni must have changed and whether each of these values has increased or decreased. Okay, so let's find these times on the box plot. So Rana was 75, which was here. So this is Rana. Okay, now it takes her 35 minutes. So 35 is now here. So Rana is now below the median. David so David did take 60, he now takes 33. So David was here, he now takes 33 minutes, so that is about there. So we can see that this isn't going to affect the least value, so 20 is going to stay the same. It's not going to do anything to the lower quartile. It's not going to do anything to the two outliers all the way over there. So what is it going to affect? It's also not going to affect the longest time. So the two bits it's going to affect are the upper quartile and the median. How is it going to affect them though? Well, we've moved two pieces of data that were greater than both of them to now a place where they are both lower than the median and the upper quartile. So that means both the median and upper quartile decrease. Cool. Okay, question 5, the final stats question, which is good because I hate stats. The lifetime L-hours of a battery has a normal distribution with mean 18 and standard deviation of 4 hours. So straight away, let's be writing that down. So L normally distributed 18 4 squared. Cool. Okay, then we're told Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. How sad. Part A. Find the probability that a randomly selected battery will last for longer than 16 hours. Okay, 1 mark. Okay, so our calculators can do this for us. So go into distribution, then you want a normal CD, put in the lower bound as 16. Put in the upper bound as something huge, so I've used 1000. Put in sigma is 4, mu is 18, and you will get 0.6915, depending on what degree of accuracy you go to. Okay, then part B for 5 marks. At the start of her exams, Alice put 4 new batteries in her calculator. She has used her calculator for 16 hours, but still has another 4 hours of exams to sit. Find the probability that her calculator will not stop working for Alice's remaining exams. Okay, so we know up to here our calculator has worked for 16 hours. So the probability that we want the probability that the lifetime will be greater than 20, given that the lifetime has been greater than 16. So, for this, I'm going to use Venn diagrams to keep the algebra at a minimum. So, let's say this guy on the left is the probability L is greater than 20, and the guy on the right is the probability L is greater than 16. Now, what we're going to need to work out then is the probability that L is greater than 20. So we know the probability L is greater than 16. We know that is 0.6915. Now, using our calculators, do what we just did for part A, but change the lower bound to 20, and we'll get the probability L is greater than 20 to be 0.3085. Okay, so we know that we know the probability L is greater than 16, given it's greater than 20, we know that that is 1. If the if the lifetime was more than 20, it was definitely more than 16. So, if we look at the formulas we are given, we can work out the intersection A intersection B is the probability of A times the probability of B given A. So, we then know that the probability of greater than 20 intersection greater than 16 is the probability of greater than 20 times B given A. So that's times the probability greater than 16 given greater than 20. Now that is where the above comes in handy, so we get the intersection is actually just the probability that L is greater than 20. So 0.3085. So we now know the number in here. Now we know the probability L is greater than 16 altogether, so the probability that lifetime is greater than 20, given it was greater than 16, is, well, it's the intersection out of the whole circle for greater than 16. So it's just 0.3085 over 0.6915, and that gives us 0.4461. Boom. Okay, so that was the probability of one battery surviving. We need all 4 to survive. So to get our final answer, we do 0.4461 to the power of 4, again because we need all 4 batteries to survive, and that gives us 0.0396. Cool. Okay, next up, Alice only has 2 new batteries. So, after the first 16 hours of her exams, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces those with 2 new batteries. Part C, 3 marks, wants us to show that the probability that her calculator will not stop working for the remainder of her exams is 0.199236. Okay, so let's think then about the situation in our calculator. We're now putting in 2 new batteries. Now we need those batteries to have a lifetime greater than 4 hours, and we need the other 2 batteries to have another 4 hours in them, given that they've already gone for 16 hours. So what we need to work out is, for the 2 new batteries, it's the probability L is greater than 4 squared, and then we're multiplying that by the probability L is greater than 20, given that it was greater than 16 squared. So, again, using your calculator, make sure you can get the probability L is greater than 4 is 0.9998. So we're doing 0.9998 squared times 0.4461 squared, sorry, 0.9998 squared times 0.4461 squared. Now that gives us 0.1989, the year of my birth, which is 0.199236. Go. Okay, then the final question. After her exams, Alice believed that the lifetime of a battery was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. Stating your hypotheses clearly and using a 5% level of significance test analysis belief. Okay, so first up, our null hypothesis. It's going to be that mu is equal to 18. The alternative Alice's claim is that mu is greater than 18. So what we're going to do, we're going to find the z value. So z, formula for this is given to us. If you can't remember it, so for us here it's going to be L bar minus mu over sigma over root n. So z is 19.2 minus 18 divided by sigma, which is 4, and she sampled 20 batteries, so it's over root 20. Now we are going to get for that 1.342. Now let's have a think about when we are going to accept or reject these hypotheses. So, using our distribution for z, we know that z has a mean of 0, standard deviation of 1, so our critical value is going to be here, where on the right we have an area of 0.05. So, using the inverse normal function on our calculators, so go into distribution and then 3, put in an area of 0.95, that's the area on the left, sigma is 1, mu is 0, and that will give us the critical value, which is 1.645. Now, our value for z, 1.342, is to the left of that. So, z is not in the critical region, therefore there is no evidence to support her claim, so reject H1. Cool. Now I'm just going to show you another way that we could have thought about that. The probability that L was greater than 19.2, which is the value we want to test, is the probability that Z is greater than 1.342. Now if we'd done it this way around, that would have given us 0.342 0.0892. So what that would tell us is that the region to the right of our z value, all of that would have been 0.0892, which is greater than 0.05. So again, we would reject our alternative hypothesis. Okay guys, that's it for the stats section. Hope to see you for the mechanics.